let us go on with the next topic. We will spend a few weeks on behavioral synthesis, a high level synthesis. If you remember from our overall flow of the several levels of abstraction that we had of the design, behavioral synthesis takes us from what we said was the behavioral level of abstraction. We had defined it as one in which functionality is specified, but timing and other details may not be clear. Particularly the mapping of functionality to clock cycles or control steps has not yet happened. So, that is what the main job of behavioral synthesis is. We convert from a level of abstraction where the time and clock cycle level detail is not quite clear to one in which it is explicitly clarified. The inputs, first of all, it would be the set of HDL processes that we wrote. So, there is of course an entity, an architecture and a bunch of processes inside that architecture. That HDL that we wrote is the main input to behavioral synthesis. That is the starting point, but it has to start from there and ultimately realize the entire synthesis process has to realize a circuit, a digital circuit that implements that design that we have specified. So, how will it implement it? We have to provide a component library whose elements will constitute the circuit ultimately, right. So, that component library needs to be there. Beyond that, there are several other things we may provide, most important of which is a set of constraints. Okay, so, that will specify under what condition is this design occurring. So, these constraints come from where? They may come from area budgets that you want to impose on the design. It may come from timing requirements, speed requirements of the design, power requirements and so on. These are externally imposed. These are not inferred from the design itself, right. When you write a VHDL model, it is not clear what the power budget is. So, these constraints are externally imposed and they are also inputs to a synthesis tool. Clock period is typically also imposed as a constraint, although you could have a variation of the synthesis process in which you can ask the synthesis tool to come up with a solution, and along with the circuit it also gives a suitable clock period for the design. It could be, but usually the clock period is provided as an input. And what are the outputs? At this level of abstraction, the output is not that final gate level netlist that we talked about. Remember, that is a lower level of abstraction, but here there would be a data path, what it looks like we will get to soon, and there would be a controller. At least these two components are there in the output of the behavioral synthesis. Okay. So, let us define a VHDL process that is behavioral or high level, just for illustration. We are modeling essentially only the functionality here. So, you can see that this is sort of a complex expression. There is addition, there is multiplication, there is division. That entire expression is not going to be completed in one clock cycle obviously, but there is still some value, like we had argued earlier. Just like there is a value to zero delay assignments, there is a value to these kinds of processes where a complex functionality is specified and we just have a sensitivity to a clock. No timing commitments means that we are not really saying when the addition should happen, when the multiplication should happen, when the division should happen and so on. That should be the output of the behavioral synthesis process. Okay. But the input is just an abstract description in which you have the functionality, but not necessarily all the timing level details. You could think of a refined behavioral process in which we actually explicitly make these decisions. So, there is an A plus B, there is a D plus E, right. You can see that these two additions are independent of each other and could be performed simultaneously. if you had the resources, then both of these could be executed in the same clock cycle. That is what the refined VHDL model here looks like. This is actually the same thing, functionally it is the same, but you can see that timing wise it is different. What we have done is divided time into 3 clock cycles, and in the first one we are doing that part of the computation that is highlighted here. We are waiting until the rising edge of the clock. This rising edge is just a simple function, we know how to implement the rising edge, right. This is just a function that is doing the same thing. We said clock event and clock equals 1. So, such a thing would be what would be there in that function called rising edge. Okay. Then I have the multiplication and the division. So, since this addition is complete, I now need to do these two. So, I now have the operands for doing that multiplication and the division, right, in the second clock cycle. Of course, this is still an abstraction, you may not finish a division in one clock cycle, but this is just an illustration. Okay. And finally, after this is done, the results are stored. So, these intermediate results are stored in T and S. So, that is my T and that is my S. After doing the multiplication, the results are stored in P and Q, and finally, I have that subtraction with the result, right. So, that is the multiplication and that is the division. So, this is what is going on here. This is a little more detailed, what you have on the right side is a little more detailed version of the same functionality, in which some synthesis decisions have been taken. What are those? These are scheduling decisions. These are the mapping between individual operations and the clock cycles. Okay. So, that is at an elementary level what is going on here, at least that is one of the major decisions that has taken place in the synthesis. And the output of the HLS looks something like this. There is an FSM and there is a data path. That data path would consist of those components that we pick up from the library that of course should be able to implement those operations that are there in the HDL. Okay. Then there is a controller that should make the decisions of which of these operations should happen in which clock cycle. The output should be at least this much, it can be more. So, you do not necessarily have to have only one data path and one FSM, there could be multiple data paths and FSMs and so on, but this is what the picture might look like of the output of the high level synthesis process. So, I have a bunch of components, these are arithmetic circuits, there are multiplexers here, there are registers to store intermediate data, there are control signals that go from the controller into the data path. What is their job? Their job would be, if they are going into the muxes, these are the select input of the muxes that they are going into, they would tell us whether this operand should be passed into the adder or the other operand should be passed into the adder. So, such control goes from the FSM into the data path. There may be some status signals that go in the other way. From these computations that we have, we may send some signals out back into the FSM. So, there may be a signal flow in both directions between the controller and the data path. That is what the output is likely to look like of the HLS process. This is just a high level picture. Let us go into some detail. And
in the system they will be created as files. The FSM
in the system will they be created as files? You can think of this as an HDL model. The input was an HDL, but the output is also another HDL, but now it is a lower level of abstraction. You can think of the FSM as still VHDL, but lower level of abstraction. Maybe the FSM is one entity and the data path is a different entity, right? Or it could be the whole thing is one entity, but the FSM is one process and the data path is more structural. So, you have instantiation statements composing the data path part of it. but as of now the FSM, as you can see, is still a little symbolic as of now, right. This is not a structure, the data path part of it is structure, but the FSM part of it is still symbolic. But you can think of that as two different entities, one of which is the FSM and the other is a data path. Okay, but that was just a very high level picture. Let us go into one more level of detail in high level synthesis. What is that resource library? We said that the HDL is an input, it is the primary input for the synthesis tool to start off, but the resource library is another input. Why is this another fundamental input? Because the output is going to be composed of elements that are picked from this resource library. Right. So, that library would look like this. I have a bunch of these components, maybe they are adder, RCA says it is a ripple carry adder. This is a carry look ahead adder, indicating that the library may have multiple components for what is essentially the same operation in the HDL. Right. You just have a plus in the SDL, but that could be realized in terms of different architectures in the implementation. It could be a ripple carry adder, it could be a carry look ahead adder. These different implementations have different properties. Therefore, the synthesis tool's job it is to decide which one to pick up. Right. Multiplication, memory, and so on. So, these could be a bunch of resource library elements that you are picking up from. These numbers here could tell us, for example, how many such resources are there. Sometimes we may have a constraint on what resources are there and how many of each resources we are able to use. So, it could be that we also have this information of how many resources of each type are available for us. Our function units would be adders, multipliers, comparators, ALUs and so on. I would have perhaps the number of them, but also important is the distinguishing features between those components would be visible to the user of that library. The synthesis tool is the user of that library. Okay. It could be that I have a memory, and that memory would be characterized in terms of what parameters. How many memory elements are there, that could be one, but the size of the memory, the width of the memory, how many ports are there and so on, those are some of the basic features of the memory modules that needs to be exported to a synthesis tool, so that the appropriate decisions could be taken. Beyond that, there would be other typical information that I would store along with my library elements. That would be, first of all, what function is it implementing. So, if it is adder or a multiplication or some ALU and so on, that has to be encoded in a way that the tool is able to understand and make the association between operations in the SDL and the appropriate components in the library. Area of the component, delay of the component, power dissipation and so on, these are typical properties of those components that would be there as part of the library. Yeah.
Since we are doing a high level synthesis at the moment,
yeah,
the area delay which will be differing across multiple resources, would they be notional or would they be mapped to a technology?
So, are the area delays technology specific? The resource library is typically technology specific. Yeah, this is still only part of the delays. Remember, there are other parts that are not necessarily visible at this time, but components are characterized for the maximum delay from any input to any output. That's the kind of information that would be available here when you pick up elements from a library. Let us define one very elementary operation that in some ways is the starting point of this high level synthesis, that is called scheduling. You have operations. We have indicated a graph over here, which in some ways violates the definition of a graph. Remember, you can't have hanging edges. Every edge needs to connect two nodes, but the meaning should be obvious hopefully here. What is being shown here is just a part of a larger graph. Right? But there are some operations, and that structure, what does it mean? The node represents some operation that is there in our HDL. You can always try to map these pictures that we are seeing with HDL that you would write. We do not necessarily point out the HDL all the time, but sometimes it is important to keep that in mind. Where did they come from? Where did this graph come from? It came from an HDL that we originally specified. What does the edge represent? It represents a dependency between the operations. You may have these operands as A, B, C and D, right, and you may have an S and a T and a Y, and your statement in the SDL from which such a structure might have been inferred, or the set of statements could be that you have S equals A plus B and T equals C plus D, Y equals S plus T. So, some such set of statements might have been there from which we derived that graph. Okay. But often we will skip the HDL part of it and will directly show the graph and show the operations and the algorithms that are working on the graph. But remember, they all came from an HDL that we ourselves wrote. What is scheduling then? The scheduling is taking these operations and associating a clock cycle with them, associating a timing with those operations. We did not specify any timing in these assignments, right. These were 0 delay assignments that we specified, but of course, finally these things have to be mapped into clock cycles. All the operations do not necessarily fit into the same clock cycle. Whether a new clock cycle is necessary or not, how many clock cycles are necessary, this could be part of the scheduling tools decision making process. It is an important part of the high level synthesis tasks. Okay, so all that we have done here is on the right we have divided the operations into clock periods, saying that these two operations, these two nodes will be scheduled into clock cycle 1 and that other node here, the third node, would be scheduled into clock cycle 2. Okay. Of course, this is possible assuming some knowledge about a resource constraint. So, in order to realize this, it is essential that we should have two adders. These are all adder circuits that are necessary in order to perform both of those operations in parallel. So, same clock cycle means that the operations are being performed in parallel, and therefore, you need access to two adders in order to realize that circuit. Okay. So, somehow that resource constraint was available to the scheduler, that is why it took that decision. But what if it had 3 adders? Could it have scheduled all the 3 into the same clock cycle? No. If the clock period was wide enough, maybe all of them could have been scheduled into the same clock cycle, right. The whole thing would have been just one big combinational circuit, and as long as the delay fits in the clock period, it is okay. But if not, as is the example here, where let us assume that the delay of one adder is the clock period that we are given, then the other operation has to follow the first two operations. There is a dependency that is inferred from the specification itself that cannot be violated. You cannot schedule the third operation in parallel with the first two. You have to wait for the first two operations to conclude. Why do we do this schedule? Remember, our objective in high level synthesis is to go closer and closer to the lower level of abstraction, right. So, remember, this timing was left out in the abstract description, that was the input, and we are trying to add more and more timing level detail into the design. Schedule, as you can see, if I had that graph here and I took this decision of these two operations in the first cycle, this in the second and this in the third, because of various reasons, all of which are not indicated here, but it is primarily dependent on the nature of the dependencies in the HDL itself, but also what resources are available, delay of the individual adders and the clock period that was given to us. Using all of those as the input, the scheduler decided on such a schedule. So, we have this information that in the first clock cycle, so I need only 3 clock cycles to implement my design. In the first clock cycle I should enable these 2 operations, in the second clock cycle I will enable that operation, and in the third clock cycle I will enable this operation. This is essentially an important piece of information from which the FSM can be composed. Right. What is the FSM anyway? So, you can see that in an FSM what kind of information goes. We can associate with the state or with the transitions some actions, right. So, there are conditions and actions associated with these transitions. So, let us say for now that the state S1 corresponds to clock cycle 1, state S2 corresponds to clock cycle 2, and S3 corresponds to clock cycle 3. So, such a schedule leads in an immediate way to a finite state machine, which of course, we said is one of the main outputs of the synthesis process. This is not the entire FSM, right. So, let us draw that FSM here. I have S1 and S2 and S3. That is the FSM that is inferred from this schedule in the picture. This tells us about the structure of the FSM, but some information is missing. What is missing?
The transition condition.
Yeah. So, there is associated with this transition, there is a condition. What else is there in the FSM? You have states, you have these transitions, you have the conditions. So, I need to specify these conditions, and there are actions. What would the actions be for the FSM? So, these are the conditions, I need those conditions, but there are also actions. I can associate actions with the transitions or with the states themselves, depending on whether I choose a Mealy style machine or a Moore style machine. So, there are actions here, right. What actions are we talking about here in this example? What is the output of one state?
The result of the calculation condition.
Result of the calculation. The calculations themselves are not taking place in the finite state machine. So, that is the let us go back to that the picture of an FSM and a data path. The computation part of what we have specified, with if there are additions, there are multiplications and so on, those are part of the data path. The FSM is only controlling the data path, it is the controller, right. So, the calculations that we have given, the computation part of the SDL, they go into the data path. How do you do the calculations here? There are additions, right. So, those additions that we have in this diagram, they would be actually occurring in the data path part of it. So, what is there in the controller? The controller has this key information of when the additions should happen, right, but the additions themselves happen in the data path. Okay. So, given that is the model, what would be there in the actions? The control, what are those control signals? Yes, we already saw that. Remember, the same adder might be doing different operations in different clock cycles. I can reuse that same adder to do different things in different clock cycles. So, the inputs may come from different sources for the same adder. Where they come from, that can be controlled by the finite state machine. It is the FSM that knows whether we are currently in cycle 1 or cycle 2 or cycle 3, and it can send the appropriate select signals to the muxes. So, these actions would essentially be control signals to the data path. So, and what control signals? These are essentially these mux select signals. And similarly, if there are other elements like registers, then there also we may need to send some signals of when to load a register. Fine. Actions should be clear. What about the conditions? In this example, where we have that graph. So, this is the graph that got synthesized into an FSM and a data path. What condition would go into the FSM?
Status signal and clock
Status signal. What status signal?
computation.
We talk about this particular example. You can visualize what hardware we are talking about on the data path side, right, for this particular example. What kind of hardware would it be? Two adders. Why two adders? Because we have two additions being simultaneously scheduled into the same clock cycle. I need two adders to realize this. However, some of those adders could be reused in the second clock cycle and the third clock cycles. I do not need more than two adders. I could have, but I do not need more than two. What else would be there in addition to the adders?
Registers.
I have an adder, and that adder would, well, I have two adders, but the inputs come from somewhere and go somewhere. But important thing is that adder may be shared across multiple clock cycles. So, actually inputs to one adder may come from multiple sources, right. That implies what else is there in the circuit other than the adder itself. There may be a mux, right. So, if that is the adder that is being shared, then I need muxes that have their inputs coming from different sources, right. How many inputs there would be to that mux? It depends on how many distinct places you are getting your data for, as far as that particular adder is concerned. So, that is certainly there. What else might be there in addition to the arithmetic components and the muxes? There could be registers. Why do you need registers? Values need to be stored, since the output produced in one clock cycle is being used in another clock cycle. You would need a register in this. Fine. So, that is the kind of data path we are talking about. There are other things. The picture is not complete yet, you have to take some other decisions before the picture is complete, but that is an example of what the data path looks like. Fine. So, for this kind of a data path, the control signal should be clear. Each of these muxes need to be controlled, and they are controlled through the select lines which come from the FSM. So, that is one interface between the FSM and the data path. Is there anything else that needs to be sent from the FSM? The register also needs a control signal in general. There is a load, okay, not the clock, there is a, yeah, there is a load signal to the register. So, maybe I put it there. That load signal tells the register when it should load new data into the register, because you might not be interested in loading new data every clock cycle. When it is relevant, that is when you would load the register. So, such a signal would also come from the FSM. This forms the sort of the interface between the data path and the FSM, and clearly these are the signals that can be produced as the actions of the FSM. So, that part is clear, what the actions are and what do they translate to? They translate to control signals of the data path. Fine, that still leaves us with the condition. Yeah. So, any guesses? What should we have in the condition?
Completion of an operation by the data path.
It must be
Could be
clock
given as a feedback.
This is the condition that tells us when we should proceed from state S1 to state S2. Similarly, here too there is a condition, right. Right. So, what is the condition under which we should transition from S1 to S2?
It must be clock, since the delay here, the delay adder delay is less than the clock.
Of course, for this circuit to work, for this schedule to work, it is essential that what is the relationship between the adder delay and the clock period? Adder delay has to be less than the clock period, otherwise this does not work. So, both of those pieces of information, what is the adder delay and what is the clock period, must have been known to the scheduler. Otherwise, you would generate an illegal schedule. Right? The fact that we came up with this schedule means that we are aware and have taken that decision after being aware of these delays, which is okay. According to the methodology, we said that the clock period is an input to the synthesis process, and the library elements, the details of the library elements are also visible to us as part of the synthesis process. Therefore, those at the respective delays are known. Brings us back to the question, what should that condition be?
Clock, change in clock.
A change in clock does translate to us proceeding from one state to the other. That is the association between a finite state machine and the clock. But what would you put there on the condition?
Change in output.
Carry exists.
Pardon me?
Carry exists.
If carry exists, what does that tell us? If a carry from the adder, which is it would be in the reverse direction. So, these were inputs, the control signals were inputs from the FSM to the data path. How would the FSM know that there was a carry on an adder? It is the reverse information. You have to send that status information back from the data path into the FSM. But functionally, what does it tell us? If a carry exists, then?
Depends on the algorithm we are proceeding. The operation is like if carry exists, go to S2 state.
But is that what is the meaning here? We go from S1 to S2. So, does it do you think there is a dependence on carry? The addition is done, which resulted in maybe a carry, and perhaps there is no carry. That depends on the operands, and then we go in the next clock cycle to S2. So, what condition do I put? The presence of a valid output on the adder. How do we know whether the adder output is valid or not? Change in output value from the previous value. Does that if there is no change, what does that mean? We are still working. Is the change in output on of the adder enough information to tell us that the computation is done? It might not. Who knows? Maybe the output is the same for two successive additions because the operands were the same. Operands didn't change. It's still a valid addition. It's just that the output did not change. I can't rely on either the carry or the output, the sum output of the adder. Yet it is an incomplete FSM if I don't specify a condition. Right.
Can't we have a separate status signal, like in a process a status flag is set when the addition is complete? That kind of thing.
Okay, what status signal? This circuit is so simple that you should be able to complete it. What status signal do I rely on?
So, rising edge of the clock.
On the rising edge of the clock, right. But do we put the clock here as a condition? Have you written an FSM? You have seen an FSM diagram, right? Do we put the clock there? Clock is implicitly a part of the finite state machine, whether it is a state table or whether it is the diagram. We do not put clock explicitly there. It is assumed that the system of course is running on one clock, and all these registers and state registers of the flip flop and so on, they are working off that clock. Maybe it is on the rising edge or of the falling edge, but that is external. We do not necessarily put that clock edge as a condition. Inputs. Which input?
Inputs to the adder.
Inputs to the adder are these. Right.
Depending on which input we are taking using the statement.
What are these inputs anyway? I had A, B, C, D. If you relate them back to the HDL, they are variables. Maybe they are 32-bit integers or something like that. Is there a point of providing all those 32 bits to the finite state machine? This is just a 3-state machine, which would be realized using how many flip flops? Just 2 flip flops are needed. So, what is the point of sending all those 32 bits as inputs to the finite state machine? Remember, FSM is not going to do computation, addition is going to happen in the data path.
Sir, from the register something should come.
The register has the output of the addition stored there. What would go from the register to indicate to the FSM that you should move on to the next state?
Sir, since the clock
It
is
should
always
by default-
implicitly available, we
Yes.
can always transition, no condition is required
Yeah.
as such.
Yeah, so what do I put? The FSM is incomplete without condition
One, always
being
true.
specified. Always true means 1.
Yeah, matlab,
What variable is 1? So, if there are inputs to the FSM, right, remember the state table, I have present state, next present state inputs, next state and outputs. These are my state table. Conditions are realized in terms of the inputs to the FSM, and actions are in terms of outputs of the FSM. So, you are right that I should proceed from state S1 to state S2 irrespective of what else is happening, yeah, which means that what do I give here if the inputs I should have do not care. What are those other inputs anyway? Outputs are clear, these would be the select signals of the muxes. Inputs as of now we did not need it actually, but there may be some status signal. The carry out for example might be useful, as of now it is not useful. Right. The fact that the scheduler took the decision of scheduling an operation in a clock cycle means that it is guaranteed that irrespective of what the operand value is, the operation will finish in one clock cycle. You do not need anything from the data path to tell you that you should move forward into the next clock cycle. There is nothing needed. Specifically the values on the sum or the outputs of the adder do not tell us that the operation is finished or not finished. But in fact the scheduler has made that decision, it was made accessible, this key information of what is the max delay through the component, the adder component, that was made accessible to the scheduler. So, there is nothing else that is needed, at least for this simple FSM that we have inferred from that schedule. In fact, you do not need any input from the data path, and therefore, whatever the inputs are as of now this would be just a do not care. That transition would correspond to a transition corresponds to a row inside the state table, right. So, that would correspond to a do not care. So, this is a do not care. Actions are these. So, hopefully, we understand how to complete the FSM. So, two things, one is that at the end of the schedule you have the structure of the FSM, it is in the complete FSM, but you know for example how many states are there, and then you have to complete it though. We are saying that we need these values, as of now I do not know what those values, I have to do some other things to send the appropriate control signals here. So, the outputs are not yet decided, but if the FSM is linear in this way, then the conditions are all do not care. You always go from one to the next. You can see that this is what kind of an FSM, it is like a counter, right. You are just going from one state to the next state without any. A counter is an example of such an FSM. The clock is an input, but there is no other input unless there may be a reset kind of input, but otherwise from state 1 you go to state 2, state 2 you go to state 3. But that is not all, like we said a few other things are missing, let us complete those. There is this step of function unit binding. Start from the schedule that we came up with, right, and now we have to take a decision of how we will implement each of those nodes in the graph. We have implicitly assumed here that the input will be stored in the form of a graph. What it looks like we will get to later on, but you can see that here just informally a node represents operations and edges, I did not draw them here, but these edges represent dependency structures. That is important information for the scheduler, because the scheduler needs to take these dependencies into account before deciding which one should go into which clock cycle. Okay. But I may have a choice, given one of those nodes, I have to now look at the resource library and decide this one, this node would be realized in terms of that component, okay. That node would be realized in terms of that other component, this is the carry look ahead. How to take that decision is a different matter. So far we are just saying what is happening in each of the steps. Of course, we introduced schedule, but what is the algorithm for scheduling, that we did not say, that will come later on. What we are doing now is quickly going through the different passes of high level synthesis to understand what happens in each pass. How it works is a different question that we will get back to later. Okay. So, this decision happens as part of the function unit binding step. Each of those nodes that are being scheduled, each of those operations that are being scheduled, we have to map them to an appropriate component in the library. That is the function unit binding step. Right. So, here the decision that we have made is that there are two adders, one of this type and the other of this type, and these two operations would be mapped onto the same adder. That is what that color coding is indicating. Same adder here is the ripple carry adder, and that other operations would be implemented on that other component. Why it is a different matter? There is an algorithm that would be deciding it, but this is the end result of the function unit binding step.
So since there is only one adder, how is supervision like? One add RC only is written, right?
Yes, but remember that I have scheduled some operation on that adder in the first clock cycle. In the second clock cycle, I am reusing that adder to do something else. That is all right, right. I still need only one component. I am reusing it in time, which is okay. In space, I can't reuse. If in the same clock cycle, I need multiple operations to be performed, I need them to be performed on different components. But across clock cycles, I can reuse components.
Sir, if these
Yeah.
are just functional blocks, can we not just use two copies of it in the same clock cycle?
You can, it is just that for this particular example, we decided that I will permit the tool only one adder of this type and one adder of that type. How many to use of each type is also a decision that the synthesis tool has to make. We will talk about the actual problem formulation for the synthesis tool, but we are just saying that as of now this design was chosen. Why it was chosen is a different matter. Obviously, that is not the only way to realize the design.
Excuse me, sir.
Yeah.
So now, like we are seeing that synthesis output gives us a FSM and a data path.
Yes.
So, but somewhere down the line, we'll have to convert this FSM also into some hardware.
Yes, indeed. Like we said, the FSM is still symbolic. That is not a circuit, but the data path part of it looks more like a netlist. This is instantiation of components from the library, and there is interconnection. A lot of those parts are clear, but the FSM part of it, you do need to take it through further synthesis steps. But that would be a little lower level. We can put that in an RTL synthesis discussion. But yes, we do need to take that whether it is a diagram or a state table, however it is that we have specified the FSM, we need another step that would take us from that symbolic specification into a netlist, into a gate level netlist in terms of flip flops and gates. But that is of course coming. We will be talking about how to synthesize an FSM later on in the course. Okay, but an important decision being taken here is which operation will be mapped to which particular component. That is what is happening in function unit binding. You can see that this takes us closer to the data path architecture. The schedule step took us closer to the controller structure. The FU binding step leads us to at least an outline of the data path architecture. What kind of outline? It tells us the following. First of all, these two resources are used, right? These two adders are used. Okay. Then remember, there is a reuse of that adder being implied by that sharing of that adder across time, and therefore, that may lead to a mux that is inferred at the inputs of that adder. The second adder does not need a mux because there is only one addition being mapped to it anyway. Okay. Now, I have the adders, I have these muxes, again they are possible muxes. What else is there? What kind of multiplexing I need to do? This adder, right, this adder needs to perform A plus B in one clock cycle. In the other clock cycle, it needs to perform E plus F, right. So, that is what. So, I need to be able to send A and B in one clock cycle to the adder, and I need to be able to send E and F in a different clock cycle to the adder, which means that I could have a structure like this, 2 muxes at the inputs, and A and B are one input each to the 2 muxes. So, that in one clock cycle I can enable that path, and I can also simultaneously enable this path, leading A and B to proceed to the adder. In the other clock cycle, I need to send E and F. The select inputs to the 2 muxes need to be coordinated, so that the correct set of operands are arriving at the adder in the same clock cycle. Okay. I need to send E plus F, E and F in the second clock cycle. Now, where are E and F? I performed these 2 additions, right, in the first clock cycle. At the end of it, I could store them in a register, right. The outputs are stored in a register. Those are my E and F. So, I need paths to be provided, this path and that other path, from the register into that second input of the respective muxes, so that E and F could be simultaneously forwarded to the adder in the second clock cycle. So, hopefully this design is clear. I am performing only C plus D in the second adder, so there is no multiplexing that is needed there. Actually, most of our design is complete here. So, that FU binding is an important logical step that needs to be performed, which helps us get closer to the data path architecture.
There will be constraints on muxes also, like muxes are.
There could be constraint. Where do we get these muxes from? We said that we pick up the adders from the component library. Muxes we would also pick up from the component library. It would usually be parameterized in some way, because it is hard to decide in advance what kind of muxes I should use. As it turned out, here I need 2 to 1 mux, but if the, you see that if the level of sharing was 3-way, then I would need a 3 to 1 mux, right. So, there would be different kind, either I have 2 to 1, 4 to 1, 8 to 1 and so on, explicit discrete components of the muxes, which are there in the library. It could also be that I have a generator of a mux in the library, to which I give a parameter that says I need a 5 to 1 mux, and it will give me the associated component, but the properties of that component would also have to be generated. Say this is the projected area of such a component, and this is the projected delay of that component. We need to be aware of the delays, of course. These are also combinational logic, and they add delays there. So, but we will get back to the implication of the muxes, particularly as far as timing is concerned. It is a very interesting question, but for now let us just say that the muxes are just inferred from the selection and the sharing decisions that are made in the FU binding step. Okay. Finally, there is a register allocation step that needs to be done. So, let us assume that these A, B, C, D are inputs to the design. So, in the entity they are input ports. Okay. So, the values come from somewhere, we do not need to worry about it, but I have these outputs from intermediate stages, intermediate clock cycles, that are used as inputs to operators in the subsequent clock cycles. That means that I need to store them in registers. How do I infer the presence of registers from a schedule? Essentially, if you have an edge, a dependence edge like that crossing a clock cycle boundary, then that implies there is a storage that is required, because I may be using that component for something else in the future clock cycles. I need to store the values. That implies registers. What kind of storage we are talking about? These are register storage. So, I need in general to assign these variables. Remember, these variables are inferred irrespective of whether or not you explicitly had them declared in the code, right. So, you could have variables of this nature. I have them as signals now. but in fact even if they were process variables, the treatment would still be the same as far as the synthesis is concerned. So, it could be that you have this E and F being explicitly declared in the code. It could also be that you have a statement like this. Okay, let us say I have T equals A plus B, Y equals T plus C plus D, and you have the output which are not labeled here, but they would be Z equals T plus Y. Or let me change this to E. Instead of Y, let us just call it G to be consistent with the picture. Fine. So, I have the E and the G being explicitly named here as intermediate signals, but that F, which corresponds to just the C plus D, right, that is not explicitly named. It is something that is inferred. It is just some temporary variable that the synthesis tool has internally created. That too needs to be stored. So, I have variables that are either explicitly declared or they are implicitly inferred. If you have a complex computation all as part of a large expression, you need to break them down into smaller units, some of which may need to be stored. Okay. So, if you have these dependencies crossing clock cycle boundaries, then there is the need for inferring a register, they need to be stored. The question of course is that I have E, F and G being such variables that need to be stored here, 3 variables, but there is an interesting register allocation problem that arises, where I make the decision of storing these variables in registers, because I need to ask this question of how many registers are needed. In this example, how many registers do we need to store those 3 variables? I can have 3 registers of course, but I do not need all of 3 registers. How do I decide how many I need? Why would I be able to do with less than 3 registers? Registers can be reused, just like those data path elements, those ALUs were reused because they were freed up once they did their job in one clock cycle. In a new clock cycle, you could use it for some other computation. The same logic applies to registers also. The same register that was used to store F at that clock boundary for this duration, it is freed up in the next clock cycle and can be used to store something else. So, that leads to an interesting problem to be solved. I have a bunch of variables in the design that has already been scheduled, and now I need to infer a bunch of registers. What is the mapping between variables and registers that possibly minimizes the number of registers I use? Could I have reused the same register for E and G? The same register could not have been reused to store both E and G. Why? Both of them need to be stored at the same time. So, somehow I need to develop a formulation where this idea is formalized a little bit. When do you need 2 variables at the same time? If you need 2 variables at the same time, then they have to be in distinct registers. If you do not need them at the same time, then you could share registers. So, we started off with scheduling as an important step. That step helped us in getting the FSM structure, at least part of the FSM structure. We could not complete the FSM, but at least we got most of the structure of the FSM because of the scheduling. Then we did function unit binding. That step helped us arrive at most of the data path components, at least this part of the data path, the resources, computation resources part of the data path, and these muxes at the input of those data paths. But finally, there is a register allocation step that helps us arrive at these decisions. How many registers do I need, and what are the variables that should be stored in each of those registers. These are sort of the three major steps in high level synthesis, but with the FU binding and the register allocation, your data path is complete. Okay. What else remains after this? Our FSM was not quite complete. We had the states, we had their transitions, and we did have an idea about the conditions. As of now, those are simple don't care conditions, but the outputs actually I need to provide the right select signals into the muxes. So, there are a few other things to complete the hardware. The mux select signals need to be decided, which resource should be connected to which input of the mux. The order is important, right. So, those I need to decide, and correspondingly I need to fill in the details on the FSM action table. In general, I need a bunch of ALU function signals. What are these? A given ALU may be capable of doing more than one function. The adder that we saw was just doing adder, nothing else. So, there is no other function input in there, but an ALU may be configured to do an addition in one clock cycle, subtraction in some other clock cycle, a comparison in a different clock cycle. So, you need a few other bits here to say in that clock cycle what should this ALU be doing. Okay. So, that is what we call a function. Where does this information come from? From the FSM. It is the FSM that knows what is the operation that should be performed, and now we also know which ALU should be performing this. So, that these bits should be coming from the FSM. Then there is this load input of a register. At every clock cycle you do not necessarily load a register with new data, only when you have data that is useful, then you need to store it. So, that information also needs to be provided by the finite state machine. So, that is the other part that is necessary for us to complete the hardware. So, these control signals would be generated by the FSM, bringing us back to that picture. Hopefully, this high level overview gave us an idea of what are the steps and how they help us in getting closer to the hardware. Of course, the step is still there, that FSM is symbolic. This is not quite a netlist. This part is of course closer to a netlist. These are just instantiated components, and the interconnections are also clear. Here they are not clear, but that is something that we already know how to do. Given an FSM, you know how to ultimately translate it into a circuit with D flip flops and gates. We will get there, but that part is already familiar. So, the process of the inference of the FSM is what is the part of the HLS task. Then let us get back to the status signal. When is this useful? It was not useful in this particular example we had. So, but when will it be useful?
If one operation takes more than one clock cycle.
If an operation takes more than one clock cycle, what kind of status signal is useful?
So then we would need to tell the FSM when to switch to the next stage.
If an operation takes a variable number of clock cycles, then there may be a need to perform a handshaking where that component actually sends a signal saying it is done. However, if that component takes a fixed number of clock cycles, if I know that it will take 3 clock cycles and no more than 3 clock cycles, then I do not need to rely on that status, right. What can I do on the FSM side? If I know that a component takes exactly 3 clock cycles, then
Count the clock cycles.
if this was my first state, there were other states before, I just introduce 2 more clock cycles, right. If it was taking 3 clock cycles, I know it is taking 3 clock cycles, then I just introduce 2 more dummy states in the FSM, okay, and pick up its value later on. Well, anyway, the FSM does not pick up the value. the values probably are going as the output and back into the input of some other component, it only sends the control signal. But if it is small, then the way to incorporate that in the FSM is to just have the right number of states, wait for the right number of states. You do not need an explicit counter there. But if the number of states is likely to be large, number of cycles is likely to be large, then perhaps there is an explicit counter that could be incorporated, and that counter could be there in the data path. The counter is a data path element really. So, again the counter may have an output signal that says it is done or whatever. If you are counting up to 10, at end of 10 you may send a signal that could be a status signal that goes back to the FSM. That is one kind. What other kind of status signal might be useful for us?
Multiple states, I mean if 58 leads to multiple states.
Right. If you are in one state and while these were linear structures that we saw so far, the structure might not be linear, right. You may be, the next step may not be obvious. So far the next step was obvious and therefore that condition was actually do not care here. But it may not be obvious, you may be dependent on something that is the result of the computation from the data path, right. It could be that you have a comparator on the data path and the output of the comparator says true or false, and depending on whether particular output is true or false, you may go one way, or let us say that input is taken here as x, then on x you go to one state, on x bar you go to the other state. Okay. So, that is the other kind of status signals that we are talking about. The moment you have an if statement, the moment you have conditionals in the HDLs, the chances are that they may translate in the FSM to a forking structure like this of the FSM. Right. So, and that condition under which you are going the one way or the other may be dependent on some input that is externally an input to the entity itself, or it could to the entire design itself, but it could also be an input that comes as a status signal from the data path side of the computation. It could be a result of some computation that happened in the previous clock cycle that is used to achieve the fork in the FSM. Okay, let us conclude here.